Reit, helo, croeso nôl. So, lle, ydych chi wedi gweld yr fideo ar yr arbrawf a be oedd yr arsylwadau. Dyma nhw yr casgliadau oedden ni'n gwneud. Here are the conclusions from that experiment. Mae'n arbrawf mae'n ffenomenon sy'n ymwneud â gwefr a negatif yn unig. Okay, so, it's a phenomenon that only involves negative charges. Electrons. Mae o'n... Sorry. Oops. O'n i weld di'r hewi. Here we go. Mae'n digwydd mewn metal zinc, ond ddim efo chromium. So, mae'n rhywbeth i wneud efo'r natur yr metal ei hun. So it happens with zinc, but doesn't with chromium, doesn't with aluminium, doesn't with steel. It would happen with sodium, potassium, and so on. Actually, efo sodium, potassium, mi fysa fo'n digwydd hefo gola glas gweledol, visible blue light would show the same effect if you had lithium or potassium. Whereas visible red light wouldn't. So there's a cut-off somewhere in the visible spectrum for those metals. Dwi'n gallu danos hynny achos basically mae'n oxididio yn syth, so sorry fod mewn vacuum. So I couldn't show that experiment with lithium or potassium because they oxidize so quickly. So you'd have to cut it, charge it, and by the time you've done that, there'd be a layer of oxide on there, so it wouldn't work without having a vacuum or something to stop it oxidizing, basically. So i'r zinc, mae o'n digwydd, i'r zinc, mae o'n digwydd efo gola uwchfioled, ond dim efo gola gweledol o gwbl. So with zinc, it happens with UV light, but does not for white light, which contains all the visible colours. The next point, chi'n rhan o wydr, nes i'n gwneud hyn, I didn't show this in the experiment, because, well, if you put a sheet of glass between the UV source and the zinc plate, then that would also block the effect, because glass is opaque to ultraviolet light. Dyna pan ydych chi'n gallu cael lliw hael os ydych chi'n eistedd mewn conservatory. So, dydy'r gola uwchfioled yn gallu dod drwy'r gwydr. So, a wedyn, y ffaith bod rhaid i'r gwefran negatif gael ei allyru o wyneb y zinc mwyn dadweddu'r electroscope. So then galw hynna yn allyriad ffotodrydanol. Okay, so the fact that the negative charges are expelled from the surface means that the discharge of the electroscope, we call it photoelectric emission. Da ni'n galw'r electrons eu hunan yn photoelectronau. Okay, the electrons that are emitted, we label them as photoelectrons. They're just normal electrons, it's just that they have been caused by the photoelectric effect. So we say they are photoelectrons. Right. So, next slide. Mae gen I rhyw sketch bach yma. Okay, so we have a zinc plate here, and on that zinc plate we have extra electrons. Okay, so mae'n cael ei wefru in negative. It's a negatively charged zinc plate. And down here, gwylod yn fama, mae gen ni 3 photon gwahanol. Gen ni'n oren, gwyrdd, a sort of violet, okay, uwch-violet di'r syniad. Okay, so, oren yn pen coch y spectrum, ond eisiau defnyddio coch achos bod fi wedi gwneud electrons yn coch, so I didn't want to use 2 things in red. So we have an orange photon, we have a green photon, which represents the middle of the visible range, and we have our ultraviolet photon. Okay, so, I ddechrau ni, sy'n ydy'r photons yn dod I fewn, cael ei amsugno gyda'r electrons, neu gledl chi, okay? Ond, the electrons ddim yn gallu jympio allan. So digon egni gan y ffoton yma I roi i'r electron I gael ei ryddhau. Okay, so this photon doesn't have enough energy to provide this one with enough kinetic energy to jump off the metal plate. Okay, so orange fails. So the green ones come in, and if this was zinc, for example, then again it wouldn't have enough energy to release the electrons from the metal's surface. Os fysa hwn, if the metal itself was potassium, then the green would have enough energy just to release the electrons. So the photon would disappear, and the electron will have its energy, if you like, minus a little bit, and we'll talk about that in a second. Okay, so pan mae'r electron, the photoelectron yn dod ar y gwyneb, dydy o'n cael holl egni y photon ond dod I fewn i'w achosi fo gael ei ryddhau. So the electron, the photoelectron doesn't have the total energy that the photon provided. So we'll talk about photon energy in a second. Reit, yn ola, so zinc di hwn, uwchfioled, hitio'r electron, a mae'r electron yn cael ei ryddhau. Right, I said I would talk about the energy of a photon. Lle ydych chi'n cofio Max Planck, pan oedden ni sôn am spectrum SER, when we were talking about the stellar spectrum, the black body curve, we talked a bit about Max Planck's work where he solved the ultraviolet catastrophe by quantizing energy. So his work essentially, basically, told us that the energy of a photon is equal to a constant called Planck's constant. Yeah, lle mae'r egni yn hafod I cysonyn, o'r enw cysonyn Planck, H, lluosi hefo amledd yr photon. Okay, so this, oops, yn ei hwnna'n sydyn o'i gilydd, o bod ni'n cadw nhw'n ei gilydd. Okay, so this is the photon energy, okay, the energy of that photon. Mi fedrwch chi ailsgwennu fo'n herm atomfedd. Okay, so remember that. Do this very quickly over here. So, yeah, sure. C is F lambda. Bianydd gola ydy amledd lluosi fo tonfedd. So mae amledd, the top frequency is equal to the speed of light over the wavelength. Okay, and we can substitute that in over here for this frequency. Dwi'n ni roed yr mynegiad yna I fewn, ac os da ni'n gwneud hynny, mae gen I hwnna'n hafod I HC over lambda. Okay, so the smaller the wavelength, these two are constants, cyfa ddau yn gysonyn. Lle y lleia ydy'r tonfedd yn fama, mwyaf fydd egni y photon. Okay, so the smaller the wavelength, the higher the energy of the photon, which explains why ultraviolets can provide more energy than visible light. Okay, so so ni symud draw i'r sleid yma. Mae hwn yn eich nodiadau chi fyd, okay, this is in your notes, but I thought I'd use it here because it gives us all 4 possible scenarios of what could happen. So, beth gyda ni fan yma ydy gola, photons gola hein, well, nhw'n symud yma. These photons have enough energy to release the electrons, okay, so they are ultraviolet, let's say, in the case of zinc. Felly, mae gennych chi'r photon yn dod I fewn. Yn y cyntaf, mae'r electron yma bron iawn ar y gwyneb yn barod. So, diolch eisiau llawer o egni I gael I ddenu hwnna. So this photon comes in, gets absorbed. So when they're absorbed, I'll just take them down here. Okay, a wedyn mae'r electron yn denig allan. Dydy, fel o'n i'n dweud, dydy egni hwn ddim yn hollol llawn o be oedd egni yr photon nath I achosi fo. ond mae'n agos iawn. Mewn geiriau eraill, mae hwn efo'r egni kinetic mwyaf edrych yr electrons gael. Okay, so this electron here, the photoelectron, has the maximum kinetic energy that can be released with this frequency of light, with this piece of metal. Second scenario, okay, the photon in this one has to travel a bit deeper into the metal surface. Okay, photon gets absorbed, and this electron has to do some work to get out to the surface. So by the time it's out, it's only got a little bit of energy left. So mae gen i egni isel. Mae just about dod allan o'r gwyneb, ag mae o'n dyn sgyn o'n llawer egni kinetic dros ben. Doesn't have much kinetic energy left over. Third scenario, again, photon gets absorbed. Mae'n chydig bach dyfnach nag oedd y cynta yma. Lle mae o'n denig, ond sgyn o'n cweint digon o, neu gymaint o egni kinetic o hwn, so it escapes, but not with as much kinetic energy as number one. And then the final example, which is kind of trivial, but could happen. Photon comes in, mae hwn ar y surface, mae gen o ddigon o egni, mi fysa fo'n gallu denig efo egni kinetic neu peth o hwn. Ond mae'n just mynd off yn y cyfeiriad wrong, so it goes deeper into the metal. So rather than escaping, it just moves deeper into the metal, which means it's not released. So, dyna chi'r pedwar senario fedru ddigwydd efo gola. Dwi wedi pwysleisio dipyn o weithiau, dwi wedi pwysleisio dipyn o weithiau bod yr photoelectron ddim efo yr un cyfanswm egni ag oedd gen yr photon oedd yn ei achosi fo. Ag yr enw roedd Einstein ar hynna oedd ffwythiant gwaith y metal. Okay, so Einstein named that property of the metal which limits the maximum kinetic energy that these photoelectrons can have. He termed that the work function of the metal. Da ni'n defnyddio'r symbol phi yn y llythyran Groegaidd phi. We use phi, the Greek letter, to represent that. So the equation is this. Okay, felly sgynna ni'n fama. Egni kinetic, ac I ddeud y gwir, I should write EK maximum. Okay, so the maximum kinetic energy that an electron can have, one of these released photoelectrons, okay, is actually half mv squared. Yeah, rhywun peth egni kinetic. M is the mass of an electron. V is the top speed at which they can be ejected. Okay, so mass electron, fan'na cyflymder mwyaf edrych yr photoelectron gael. HF, egni'r photon sy'n dod i fewn, a phi fan'na, hon ydy'r ffwythiant gwaith. That's the work function of the electron. So, what's going on? Well, mae gennym ni analogy arall fydden ni ddefnyddio'n fama. Dwi jyst am newid ffenast dwi'n castio i chi gael i fynd yn ôl i'r nodiadau. Just a second. Okay. Right. Un ai nôl i hwnna, sorry, dwi jyst am screen. Okay. Mae hwn yn eich nodiadau chi fyd. Okay, this diagram is in your notes as well. Yeah. So mae'n eich feddwl am yr electrons. Mae'r electrons yn y gwylod yn fama. Lle mae angen lot o egni photon mwyn i hwn gyrraedd y gwyneb yn fanna. That represents the work function. it's just the minimum energy required for the electrons to be released from the surface. If you look at the definitions, there's a definition there for work function of metal. Very common question, what is work function? Or define work function. Felly, yr egni lleia mae electron ei angen mwyn dianc o arwyneb metal. Be mae hynny ddeitha ni o'r arbrawf bod dyr chromium, y metela oedd ddim yn rhyddhau efo, hyd yn oed efo uwch fioled, mae gen nhw ffwythiant gwaith lot uwch, mae'r twll yma yn ddyfnach. Okay, so for the metals other than zinc, what it tells us is that the work function for them must be larger. The hole is deeper in this analogy. So the electrons don't get out, don't get enough energy to get out. So these are the slowest, the ones right at the work function, if you like, level, are going to be the ones that just about trickle off the surface, the lowest possible kinetic energy. The ones at the top here will be moving at the maximum possible kinetic energy. So this is your equation for the photoelectric effect. Wel, yn y link can Academy, mae yna enghreifftiau, mae fideo eitha maith, mae yna lot o enghreifftiau yn fanna, a mi fyddai'n adio cwestiynau o dan hwn hefyd i chi. Reit, yr un peth arall da chi siw bod ydy'r arbrawf i fesur yr amledd trothwy yma, yr ffwythiant gwaith. Okay, so the experiment to measure this work function we'll have a look at now. So I'm going to stop presenting that and I'm going to find the, here we go. Well, actually, na, dwi'n gydanos y llun gynta. Mae hwn yn eich nodiadau chi hefyd. Just a second, paste it in. Yeah. A window, sorry, even my eto. Right, so this is your photo cell. Okay, hwn di'r ffotogell. The cell itself, y gell I hyn ydy hwn, beth sy'n y gwydr yma. Sy'n fewn I fama, mae o'n bacdod. It's a vacuum. We have our metal plate. We also have a collecting anode. Anode casglu. Ac mae gen I power supply yn y gwylod yma. Wan, cyfle enw'r pŵer yma. So, na'n just wneud yr electrons yn fama, na'n just cylchu nhw bod yn gallu dangos nhw'n neidio. So, beth da ni'n neud? Da ni sgleinio gola o amledd penodol. Okay, so we shine light of a certain frequency onto the metal surface. And these electrons jump over the gap. If they jump over the gap, they then flow all the way through. My power supply forward of mine, and you get a current reading on the ammeter. Next step is to make this side positive, terminal B positive, and terminal A negative. Terfynell B yn positif, terfynell A yn negatif. Beth sy'n digwydd wedyn ydy, mae'r electrons ma'n neidio allan, ond achos bod yr metal wan yn fwy positif, achos mae'n sownd yn y pen yma, mi na nhw'n neidio, a ella just cyrraedd fanna a cael eu tynnu nôl. Okay, so the electrons jump across the gap. Remember, this now is negatively charged. This is positively charged. So the electrons will jump across, but maybe get repelled from this side and get pulled back onto the positive plate. So then we get zero current. Then we vary the voltage so that we get very, very slight current, the smallest possible current. Okay, that means that only the most energetic ones, the ones that were close to the top, if you like, are then chaps yma, yeah, these chaps. Mae hynna just cyrraedd, just touchad a mae'n cael tiny fractions of milliamps of a current. Mae hynna'n dweud ni, well, okay, mae'r egni hynna felly, hynna oedd efo'r egni kinetic mwyaf, yeah? The maximum kinetic energy was given to those electrons. And if you look at the top of this slide, gyda ni fynegiant yn fama. We have an expression for the kinetic energy, the maximum kinetic energy, which is the charge of an electron, E, times the voltage that causes this minimum current, or actually when it actually just goes to zero. That's called the stopping potential, yeah, or potential stopio. Da ni wedi trafod yr uned electron volt, ond neu jyst danos yn sydyn, os da ni eisiau convertio o joules i electron volts, wel, EV, wel, mae hwnna mewn coulombs, mae hwn mewn joules per coulomb, felly mae E lluosydd o V yn rhoi joules. Mae'n uned handi ar gyfer gwaith ffotonau, achos bod ni'n sôn am egniaeth mor fychan, da ni'n sôn am 10 to the minus 19 range, felly da ni'n defnyddio electron volt fel y mesur. So when you look at energy levels, for example, in an atom, the energy levels are usually given in electron volts because of the scale. So you'll have maybe 13.3 electron volts. Well, let's convert that into joules. To do that, we times it by the charge of an electron. Let's see what an electron. Mae hynny yn dod â ni at, bear with. Right. Yn dod â ni at 13.3 times 1.6 minus 19. 2.13 times 10 to the minus 19 joules. Yeah, mae'n just yn safio'r gybyns yma I gyd, just saves you from having that massive, well, having this times 10 to the minus, whatever, sorry, it was 10 to the minus 18. Okay, so dyna fo'r egni yn fanna. A dyna ni ar yr effaith ffotodrydanol. I will come back and add the video about, showing an example question later on. Oops, yeah, sorry. Just scrolling sydyn I weld sgynna ni yn fama. Yeah, sorry, mae'n un bit bach arall I should drafod. Okay, there is, sorry, one extra bit that we want to talk about, which is how we get the values from the experiments with the photocell. So, mae hwn I gyd yn y nodiadau. Okay, it's all in the notes. These are all images taken from ionos. So if we plot the kinetic energy, yeah, and kinetic which we can get from EK max, the EV, yeah, mae hwnna mewn joules, achos da ni lluosi E efo V. and we plot that on the y-axis against frequency, maen nhw wedi iwsio frequency F, gewch chi newid hwnna. Mae'r symbol yma'n cael ei ddefnyddio weithiau fyd, fatha amledd. So that symbol new, is it new or mu? New. That's used for frequency as well. So this equation here, that's the same as HF minus lambda. Okay. So get rid of this. Amledd ar y chelyn X ac ignikinetic ar y chelyn Y. Ac os ydych chi'n sbio ar yr hafaliad, nath ni sgwennu gyna, Y equals mx minus phi. Wel, mae hynna'n deitha ni felly bod graddiant y graff yn h, so h here, the gradient, and the intercept, we've got a negative intercept at minus phi. Or phi, sorry. Yeah, no, minus phi, yeah. So, hwn yn fama ydy, that's the work function, and the gradient is given by, the gradient gives us h. So os gynnu ni fetela gwahanol, they have different graphs. Different metals will all have the same gradient. Let's go green. Yeah. All have the same gradients, but they will have different intercepts here. That's the different work functions of the metals. And that's the green and the orange. Okay, so the orange one could be lithium, for example. Green might be, dwi'n cofio os o potassium to lithium sydd o'r lleiad. Yellow would be maybe zinc. Okay, so that's how you analyze the results of the photoelectric, the photocell experiment. Sorry. That's it in terms of the photoelectric effect. As I say, I will be back with some questions. And yna un peth arall yn eisiau dangos chi, na i just dangos yn hwn yn gweithio. I'll put a link to this in the classroom post as well. But, hello there. I'll put a link to this in the classroom post, but I'll just show you how it works. So, are we sharing screen? Hang on. Present a window. There we go. Right. So this is a simulation of the lab. Yeah. So we're going to need a photocell. In the panel, we've got the photocell. We can control the wavelength of light that's being shown. So we can make it longer, so lower energy. Right there. We can change the brightness. And hefyd mi fedrwn ni newid yr power supply. Okay, we can increase or decrease the power supply. Okay, dwi'n meddwl bod ni'n gallu newid y metal. Hold on, we can change the metal as well. Right, let's use potassium then. Gychwyn potassium. Dwi'n dweud 0 volts yma, achos... Okay, so we've got 0 volts, so that any photoelectrons that get released from the potassium surface will travel across. So beth dwi'n mynd i neud ydy cynyddu egni gola. Okay, by reducing the wavelength, I'm increasing the energy of the light into yellow through green. Allan o gwyrdd, da ni'n dechrau dod i ochr glas y spectrum. Beth ni'n gwneud? Ni allan rhywun sy'n fawr, da ni'n altro aelod. Ond dwi'n gweithio. There we go. We've got some electrons. So da chi'n gallu gweld yr electrons yn fflio ar draws y gap. Wel, I weithio allan i egni mwyaf nhw, to get the work function, we'll need to work out the maximum energy, so we need power supply more positive. Ydych chi weld nhw'n colli ag ni wan? Can you see them? They're just not quite getting to the other side. So there we have the stopping potential for potassium in this example. We're going to need wavelength, so that would be the threshold wavelength. If we converted that into frequency, it'll be the threshold frequency. And by threshold frequency, what I mean is dwi'n bod yn siarad a ydych chi'n wedi bod yn weld o, damn ie. Sorry. An error occurred while screen sharing. Anyway, the simulation that I'll put a link to underneath, you can play around with it so that so you fully understand it. Any questions? As always, just leave a post. Yeah? So just gadwch gwestiwn ar post classroom neu na fanno di lle calla. Wedyn, be nai ydi rhyddhau yr post yma i chi at diwedd yr wsos, fel bod chi'n cael chance i just sbio ar chydig o bethau o flaen llaw, ella gwachod y fideos yma ac yn y blaen. A wedyn, yn ystod y wers, fyddai di rhannu y link ar gyfer hynny, mi fyddai'n fyw i ateb unrhyw gwestiynau. Okay, so any questions that you have about this post, I will be online live at the calendar event. I'll share a calendar event with you as I've told you how I'm going to do it. So dwi'n dechrau bablo wan, so mae hon yn mynd i fod yn fideo rili hir. Okay, siarad efo chi'n fuan. Wel,